Swayam Prabha. Digital India. Educated India.
Okay, so first of all, I would like to thank the organizers, all of the organizers, Raj in particular, for inviting me and organizing this meeting. It has been great last few days here, and I just want to once again wish Professor Satyamurthy all the best for the many more years to come. And so with that, I'll be talking about non-adiabatically driven quantum interference in ultracold chemical reactions. That is continuation of some of the work that we have been doing lately, and it is not on machine learning that Raman talked about. So I would like to start with highlighting some of the research areas we have been working on over the years. Primarily, we are interested in quantum dynamics, and quantum dynamics applied to different molecular issues in different environments, astrochemistry, atmospheric chemistry to some extent in the past, and also looking at how one may control the outcome of chemical reactions. One such approach that has recently been explored is through stereodynamic preparation of the initial molecular alignment and orientation. And there have been some really interesting experiments done in Dixer's group, so we have done quite a bit of work related to that. And over the years, over more than 20 years, we have been looking at molecular collisions in the cold and ultracold regime, motivated by recent interest in cooling and trapping molecules and using cold molecules and ultracold molecules for quantum science applications. So my talk would primarily be centered around ultracold molecules and ultracold chemistry. And why it is important? It is important because if you cool down the translational degrees of freedom, and also prepare molecules in selected internal quantum state, then you have essentially absolute control of all degrees of freedom. So the techniques that have been developed in recent years, the cooling and trapping techniques and the state preparation techniques, allows you to achieve absolute control over all degrees of freedom. And so this allows control chemistry to be carried out, and the control being achieved using external electric and magnetic fields. And in this regime, when you go to below millikelvin, microkelvin temperatures, you also reduce the number of partial waves that are involved in the collision process. So the quantum effects, such as the geometric phase effects, get amplified in this regime. And so it's kind of counterintuitive that to see some of the electronically non-adiabatic effect manifest in this regime. Normally, one would think that those effects are much more revealing when you go to higher temperatures, but many of those effects get washed out, particularly the geometric phase effect, when you have contributions from many partial waves, but when you have only a single partial wave contributing, those partial wave averaging vanishes. And again, as I mentioned, one could explore stereodynamics in this extreme quantum regime and explore quantum interference effects on reaction outcomes. So I'll take a couple of examples from our recent work to illustrate this, and in particular, looking at how non-adiabatic chemistry manifests in the ultracold regime. So I'll take two examples, reactions of potassium atom with a potassium rubidium molecule, and a reaction of lithium with a lithium sodium. And these are kind of strange looking molecules. the bialkali dimers, and but they are kind of the workhorse type molecules in this field, primarily because it is much more easier to create ultracold diatomic molecules, ultracold dimers of the alkali systems, primarily due to the availability of easily accessible lasers. So we would, really like to have these experiments on, say, something like fluorine plus H2, but H2 is not a system that can easily be cooled to microkelvin temperatures. So by and far, the KRB molecule or the K plus KRB reaction has become more like a fluorine plus H2 reaction for the ultracold chemistry experiments. Now, preparing these molecules, preparing ultracold molecules is very challenging. There are many, several different techniques that have been developed. And one technique is that you create ultracold atoms first and then associate these atoms into molecules, either using light, that would be photoassociation, or magnetic field, that would be magnetoassociation. So magnetoassociation or the Fishback resonance method. So I just have a slide to illustrate this. So you have two, say, electronic states, and the blue one, the ground state. Then you have the red one, that would be a closed channel relative to the collisions occurring on the ground electronic state. So if you have two unbound atoms, say, approaching it from large separations, that would be shown by the energy of the dashed line here, and so with respect to the red curve here, that is the closed channel. So this would be the energy would be asymptotically closed. But then if you have a bound state here in the closed channel, and if you scan a magnetic field, then you can make this the energy of the colliding atoms in resonance with the energy of the bound state of the closed channel. And so you can convert the two separated atoms into a dimer by that process. And that is what's called magnetoassociation. And that is a workhorse method these days to create ultracold molecules. So this is how the strategy to prepare KRB molecules using the Fishback resonance method. You have rubidium-87, that is a composite boson, and these are the trapping potentials, and obviously bosons, there is no restriction on the number of particles to occupy a given energy state, and so at ultra low temperatures, all of them could occupy the ground state, and that is shown by this red potential here, and the particles shown by the red balls. Then you have 40 potassium, which is a composite fermion. And again, fermions, because of the Pauli's exclusion principle, two identical fermions cannot be in the same energy level, so they stack up in different energy levels. And then you apply the magnetic Fishback resonance, as I indicated before, and then you form a dimer. And when you associate a fermion and a boson, you get a fermionic dimer. And so again, they stack up in different energy levels. This is the KRB molecule produced. And this is an experiment done in Jun Yee's group at University of Colorado in Boulder. And so now once you have the KRB molecules formed in the absolute ground state, there is still, if they come close enough, they can undergo chemical reaction yielding K2 and RB products. But that chemical reaction has an energy barrier, and that barrier is coming from the centrifugal potential. Because now you have a KRB molecule that is a composite fermion, and when two identical fermions collide, the lowest partial wave by which they can collide is a P wave. So then you have a centrifugal barrier coming from the L equal to 1 partial wave, and that corresponds to about 24 microkelvin. But these molecules are produced around 300 nanokelvin. So that means it has to tunnel through the centrifugal barrier for the chemical reaction to occur. But it does still happen. So that is actually what is shown here, that the KRB molecule prepared at 300 nanokelvin, that is shown by the red ball here, and it decays much more rapidly than, say, molecules prepared at 65 nanokelvin, because at lower temperatures, you have less efficiency for tunneling through the barrier. So it actually, but even at this temperature, extremely low temperatures, reaction can occur through tunneling and with measurable rates. And that is really quite fascinating. And of course, we, well before these experiments were done, we have performed illustrative calculations, say taking fluorine plus H2, and many other systems showing that ultracold chemistry does indeed happen. But these experiments were, possible only systems of this kind. Now, the thing is, ultracold chemistry, obviously, itself is fascinating. It is nice. And as chemists, I would like to see chemistry happening and chemistry being studied in this regime. But molecules such as KRB or other molecules, when you are making them for quantum science applications, potentially for quantum control or quantum communication or for quantum computing, these are polar molecules. You can create an optical lattice, and in each lattice side, you can have an array of this, you can have one molecule per lattice side. And so, in fact, you can think of, an egg carton where you have, one molecule per slot. And so you could study many-body quantum effects. But the thing is, you would want stable systems where you could actually use it for practical applications. But chemistry, it is a disruptive process. And so you actually don't want chemistry occurring for these systems, because that would destroy the coherence. And so there are efforts to prevent any chemistry from occurring in these systems. That is, avoid these two, the molecules coming together. And there are some techniques that are being developed. Roman has done some important work related to behavior of molecules in electric fields. And microwave dressing is one method that is widely being used to prevent this kind of chemistry taking place. But we are now going to, interested in chemistry. And this is one of the first experiments on ultracold chemistry from the group of Jun Yi. And what you see here is, again, the 2-KRB molecule. You have that 24 microkelvin P-wave energy barrier, decay of the KRB because of the chemical reaction. And now, obviously you have collisions occurring through P-wave for the two identical KRB molecules. But if you prepare them in two different hyperfine states, a mixture of 50-50 hyperfine states of these two, then the restriction that P-wave collision should occur is lifted. And so S-wave collision is possible for the 50-50 mixture of two different hyperfine states. And in that case, you don't have the L equal to 1 centrifugal barrier anymore. So it is S-wave. And in that case, the rate is nearly 2 orders of magnitude larger than for the identical fermion collisions. So it would be something on the order of 10 to the minus 10. And you also see that the rate constants measured at two different temperatures are comparable, very similar. And that is because in the Wigner regime, where the cross-section diverges inversely as a velocity, the rate constant becomes finite. And so that is also demonstrated in these experiments. The experiments were revised by Kwong and Nee's group at Harvard in the last about 4 or 5 years ago, and with a goal of now detecting the quantum states of the products that are formed. In the previous experiment, the chemistry was inferred through basically the disappearance of the initial KRB molecules. The products were actually not detected, but they were able to set up the experiment in which not only that the initial states of the KRB were completely controlled, but they were also detect the intermediate K2RB2 complex formed, and also through velocity map imaging, identify the quantum states, 57 combinations of rotational levels of the K2 and RB2 that were produced as a result of the reaction. Now, the KRB molecules are prepared at around 300 nanokelvin. exoergicity for the reaction is about 10 wave numbers, about 15 Kelvin. And that goes into the relative translation and rotational excitation of the products within the vibrational ground state. But so again, what you see, even though it is a tiny amount of energy that is released compared to the initial collision energy of 300 nanokelvin, you are still talking about 1 million or 100 million times more energy released, more kinetic energy released in the collision process. And that is something, normally there is no chemical reaction where you have that much different magnitude in energy that is released as a result of a chemical reaction. Now, if you want to study the KRB plus KRB chemical reaction in its full complexity, including rotational, vibrational, spin, and hyperfine interaction, using quantum close coupling calculation, that is a task I think we are still not equipped to do because of the very, very large number of coupled channels involved. And but in the experiments of Jun-Yi, when they initially reported the KRB plus KRB, they also looked at the K plus KRB chemical reaction, which is an atom diatom. It is also an exoergic process leading to K2 and RB. And in fact, what they looked at is they looked at the KRB colliding with the KRB colliding with rubidium. The rubidium collision is actually endothermic, so you don't see chemical reaction unless the collision energy is about 250 Kelvin. And that's correct. And but if you have the collision partner potassium, then you see a very rapid decay of the KRB molecule due to this chemical reaction, and a reaction rate of about 10 to the minus 10 cubic centimeter per second was reported. Again, they have not measured the quantum states of the K2 formed. It is just that the decay, because there is no other decay channel available when you prepare KRB in the absolute raw vibrational ground state. So the decay is attributed to chemical reaction. So we thought it would be important to do a full quantum dynamics calculation of this reaction. Previously, people were using simple approximate methods, such as if you know the C6 coefficients, you could compute an effective scattering length based on which a universal T equals 0 rate constant could be estimated. But we are, and that assumes that all of the once the reactant come to the short range of the potential, then the reaction occurs with 100% efficiency. So we, about several years ago, started looking at this from a perspective of doing full quantum dynamics. So this is the potential surface for collinear approach. Obviously, this is just for the convenience of plotting, but we have a full three-dimensional interaction potential for this system. So KRB coming in, forming an intermediate K2RB complex, and then yielding the K2 plus RB products. So the quantum dynamics is done in hyperspherical coordinates, which is much more convenient for reactive scattering calculations. There are a lot of details involved, as Satyajit knows here. And so I just, to introduce some terminologies, I just show a couple of expressions here. So we have the radial kinetic energy term, rho is hyperradius, and theta and phi are two hyperangles. This is the angular kinetic energy term. So you expand the overall wave function for a given total angular momentum and the projection quantum numbers in terms of the hyperspherical surface functions. At each value of the hyperradius is divided into a large number of sectors, and then these surface functions are obtained by solving the corresponding eigenvalue equation, and you get the eigenenergies here, which at large separations, at large value of the hyperradius, becomes the raw vibrational energy levels of the dimers. So skipping all the details of the calculation, just want to show this is the experimental data. In this case, the experimental data corresponds to temperature below 1 microkelvin, but they have actually not specified exactly what temperature it is. But it doesn't really matter, because below a microkelvin, the rate constant is independent of the temperature. This is our result using a full interaction potential that has a non-additive three-body contribution. We also constructed a potential just to see from pairwise dimer potential to see if that can yield result in comparable agreement with the full 3D potential. And these are the vibrational resolved rate constants. And below a microkelvin, we approach the Wigner regime. So what I want to highlight is that the experimental data is about 50% higher than the predicted value from our calculations. And on the right, you see the what we call the exact quantum calculation, same as the black curve here. And the red curve is what is that universal model based on the C6 coefficient, which seems to be in very good agreement. And then we have a jet-shifted quantum calculation compared to the universal model that include all J's, but not that relevant here. But the thing is, we do have some discrepancy with the experiment, and there could be many different aspects. We have not included spin-or-hyperfine interaction in our calculations, but also, if you look at the electronic potential surfaces, the reaction does not occur on a single electronic state. There is an excited electronic state that undergoes conical intersection with the ground electronic state, and the green curve here is that seam of the conical intersection. So a full quantum dynamics calculation must include effect of the excited electronic state. And that is not an easy task for systems like this. And typically whenever when you have electronically non-adiabatic effects, the better approach is to use wave packet methods. But wave packet methods are not convenient to use at ultra-low collision energies, though some attempts are being made. And so, again, this is the same thing, but at a different, plot. What I want to illustrate here is the cone of the upper electronic state. And in this case, it so happens that you start with the KRB molecule in the lowest vibrational rotational level. And at that energy, the cone of the upper electronic state is accessible, even though the asymptotically the upper electronic state is at much higher energy. In the interaction region, the cone of the upper electronic state is accessible. So that is shown here in terms of these hyperspherical adiabatic energies. These are the same adiabatic energies that I discussed earlier in solving the surface function Hamiltonian. So you have the KKRB, vibrational ground state, rotational ground state. This is the energy. So this is the entrance channel. You see a lot of gray curves here. They are all the various raw vibrational, asymptotically correlate with the raw vibrational energy levels of the KRB or the K2 molecule. The blue curves are every 100 of the gray curves. And so they correspond to the lower electronic state. You saw the adiabatic curves on the upper electronic state. So you can see as you come in the entrance channel, even with an extremely tiny kinetic energy, many of these adiabats are energetically accessible. So that means this is an inherent, even in the ultracold limit, this is a coupled electronic state problem. And so the formalism, the time-independent quantum approach to do non-adiabatic dynamics has not been developed until recently. In fact, it is Kendrick who formulated the problem in hyperspherical coordinate, and our work is in collaboration with him. So now we use a diabatic approach in which the coupling between the two potential surfaces are in the off-diagonal part of the potential matrix. So you have the V1A and V2A are the adiabatic potentials, and then through the adiabatic to diabatic transformation, we get this diabatic potential matrix. So skipping all the details, this is the same as I showed earlier. This is the result of the 2x2 calculation. When I say 2x2, the calculation is including the two electronic states compared against the what we call the NGP is no geometric phase. I think a better terminology actually would be a adiabatic calculation. So the V1, the blue curve, is the same blue curve here. The red curve here is the lowest of the adiabatic potential on the upper electronic state. And you can see, if you are able to see, there is some tiny difference between the blue and the red curve. Red curve is from the 2x2 calculation in the region of this conical intersection. And as you move to larger values of the hyperradius, the difference between the adiabatic and the 2x2 curves becomes very small. And that is because now you are outside the region of the conical intersection. Now, my time is almost running out. So these are the results from these 2x2 calculations that are resolved, rotationally resolved cross-sections for vibration levels 0, 1, and 2. And finally, we have the temperature or the energy-dependent rate constants. You may not be able to see all these things. The black curve here is the previous single surface calculation. The red curve, there's a full red curve here. That is a new 2x2 calculation, which seems to be in the right direction, closer to the experiment. And but once you go about 10 to the minus 3 Kelvin, then all of these results kind of merge together. That means these differences are amplified in the ultracold limit, and that is in part because you have interference of wave functions. That is, you can think of two paths, a direct path and a path that goes around the conical intersection. And the path that goes around the conical intersection, intersection has a geometric phase associated with that. And the effect of the geometric phase is to change the sign of that interference term. So this is a different reaction, but very similar, lithium plus lithium sodium, where we have illustrated that interference effects. And in fact, if you look at the rotationally resolved rate constant, the 2x2 calculation is the red curve here. The single surface calculation is the black curve. And once you go to higher temperatures, you have, there is really no difference. But that the interference term really becomes significant. Now you're seeing an order of magnitude difference between the adiabatic and the non-adiabatic calculation, and it is because of that quantum interference introduced by non-adiabatic dynamics. So I'll skip this. This is rotational distribution. Just want to say, but once you actually sum over all the rotational levels and all of the vibrational levels, then some of this interference effects vanishes. And so between the 2x2 and the single surface calculation, you don't see that much of a big difference. Still, there is some difference. And this would be what the universal model would predict. So in this case, the reaction is actually not fully universal. So let me just wrap it up. Oh, by the way, you can't read any of these things. This is a recent experiment from Wang and Ni's group on rubidium plus KRB collisions, where they prepare rubidium in an excited hyperfine state. And after the collision, it comes to a lower hyperfine state. The energy released can actually pump 3 rotational levels of KRB. And they compare the experiment against a calculation that includes everything except the non-adiabatic dynamics. And so the theory and experiments do not fully match. And they suspect it is because it is because the non-adiabatic dynamics that I just described also applies to this system, and that might be the reason for the discrepancy. So with that, I like to thank my collaborators, Brian Kendrick, one of my very durable long-time collaborators, and Svetlana is the one who computed the potential surfaces for KRB, the K plus KRB and the lithium plus lithium sodium. And I had wonderful postdocs over the years. James Croft worked on the single surface KKRB chemical reaction. Jisha was involved in some of the geometric phase calculations, not on these systems, but some other systems. And Humberto, who is now a postdoc with John Bourne at the University of Colorado in Boulder, is the one who did the non-adiabatic calculations on the K plus KRB reaction. So with that, I would like to thank for all of your attention and again, giving me an opportunity to come to this meeting. Thank you.
Swayam Prabha. Digital India. Educated India.